Welcome to Revolution Against Evolution. I'm your host, Doug Sharp.
And Rich Gear here as well as your co-host, and we're here we're going to talk about something that gave Darwin conniption fits, actually, and it's the human eye, right? Or just the eye in general.
The eye in general, the human eye. We're going to talk a little bit about the mammal eye versus the eye of the octopus or the squid or something like that. And we're going to set out to show that this claim that Dawkins and a few other anti-creationists talk about is that it's a poor design.
What's interesting, Doug, about this, just to go back to square one there, Darwin was worried about it because of the complexity alone.
Right.
Poorly designed or not, this thing could have never, I mean, the idea that we use the word design, Doug, indicates something that isn't just random chance and accident. But they've shifted it now from the complexity to show you it was badly, that because of all the inefficient ways that it came together, now it's badly designed. I said, well, but the fact that it was designed is still being used, but it's not badly designed, because we're going to show you in a little bit of time here. Doug's going to go through a whole litany of things of why it's not badly designed, and what are some of the optimal things, Doug, that just it makes it work better than anything else, basically, the way.
Well, we're going to set out to show that this claim by evolutionists that the eye is poorly designed, it's totally irresponsible to say this, and it's unfounded. And I have a book here that I'm taking a lot of my information out of, which is a new book by Jerry Bergman. In fact, I think this is maybe a pre-release copy. So look for it on Amazon. It's probably going to be available in the next few months or so. But I got an evaluation copy, and this is chock full of excellent information. And it takes this claim that poor design, and it shows that it's an invalid argument against intelligent design.
And that's the name of the book, Poor Design?
Poor Design, right.
Is there a question mark after the end of it?
Well, but it should be.
It's sort of indicated there anyway, but the context of the book,
Now here's what's claimed by the evolutionists. I'm going to read some of these quotes from the evolutionists.
Yeah, we're doing the negation of cinema. We're going to read you in front of the camera. But
that's right.
To get it all together, you kind of have to do this.
Basically, it's the claim that the photoreceptors for the eye are put in backwards.
All right, inverted.
Inverted, and so that's the so-called placement of the photoreceptors, and they say this is the most common examples of poor design in the mammalian retina, and it's a highly sensitive organ located in the back of the eyeball, and the claim.
What is it called again?
The retina.
Oh, just the retina. Okay, I thought. Okay.
Yeah, and it's particularly the photoreceptors in the retina is backwards. Instead of having them pointing in front in the eyeball where they catch the light
like this
as they come, they're actually backwards. And I'm going to talk about that. It's pointed away from the incoming light. And Michael Shermer, he's the guy who says it's built upside down and backwards, with photons of light having to travel through the cornea, lens, aqueous fluid, blood vessels, ganglion cells, amacrine cells, horizontal cells, and bipolar cells before reaching the light-sensitive rods and cones that will transduce the light signal into neural impulses. Okay, so then Richard Dawkins, he says, an engineer would naturally assume that the photocells would point towards the light, with the wires leading backwards toward the brain. He would laugh at any suggestion that photocells might point away from the light with their wires departing at the side nearest the light. Yet this is exactly what happens in all vertebrate retinas. Each photocell is in effect wired in backwards, with the wire sticking out of the side nearest the light. The wire has to travel over the surface of the retina to a point where it dives through a hole in the retina, which is the so-called blind spot, to join the optic nerve.
Yeah.
Now, here's what he emits too. He says the light entering the eye, instead of being granted an unrestricted passage to the photocells, has to pass through a forest of connecting wires, presumably suffering at least some attenuation distortion. Actually, probably not much, but still it's the principle of the thing that would offend any tidy-minded engineer. And so that's what...
You know, Doug, just to stop you just for a second, just as a common sense thing, we actually have, even on our set here, we always turn the lights a little bit away from us because it gets too intense. It kind of messes up things. I have lights that reflect. I know most people, maybe people out in the audience, Doug will have lights that they'll shine up to the ceiling rather than having directly shine at you because it mutes some of the harshness of it. Is that anything to do with what we're talking about, maybe, or not?
Well, there's a lot of things. Basically, what is passing through is actually shorter than a wavelength of light. So even one photon of light is enough to elicit a response, an electrical response. And a cluster of 5 photons produces a spot which is visible in the eye. And we get millions of photons hitting us all the time.
Right.
So
You'd be almost sensory overload if you had all of them right in on you. You couldn't even put it together. Although I have to admit, Doug, we technically see upside down. When I did an exhibit years ago dealing with cameras and the advent of learning how that stuff, they had to figure out how to make when you took because camera obscura does that very same thing. The light comes in and it flips it.
Right.
And then they've learned with cameras they have like mirrors and they would flip them. It would flip, but that's what our mind does. There's no comments here about how incredibly adaptable the brain is to see the upside down image and immediately convert it to a right side up image.
Right. That's what
they never talk about that. To me, that alone negates their argument. But let's just go purely back to the idea of the eye. Jerry's going to go into the things of why that's not a bad design. You start to go into how little light you need to actually get a response or an image response. But
they admit that the eye's design is brilliant, but it betrays its origin with a telltale flaw. The retina is inside out. The nerve fibers that carry the signals from the eye's rods and cones, which sense the light and color, lie on top of them and had to plunge through a large hole in the retina to get to the brain, creating the blind spot. No intelligent designer would put such a clumsy arrangement in the camcorder, and that's just one of the hundreds of accidents frozen in evolutionary history that confirmed the mindlessness of the historical process. So you see what's going on here. It's basically accusing God of being
bad designer. So
bad
therefore it
designer.
couldn't have been designed. It's an accident. Okay, all right.
Okay, even a bad designer is a designer, right? But in this case, we have not been able to produce a camera that has the sensitivity that the human eye has.
Right, okay.
And so the eyes of the lowly squid, which the nerves artfully hidden behind the photoreceptors, are an example of design perfection. If a creator had indeed lavished his best design on the creature he shaped in his own image, creationists would surely concluded that God is really a squid.
Okay, all right.
All right, so let's take this to task here a little bit.
Let's unravel this, okay.
And what happens is that this verted design, which is what the squid and the octopus have.
The verted as opposed to inverted, what we have.
It's more optimal for the aquatic world. But there's let's take that for example, a problem of design. How did it transition from the verted design to the inverted design?
Yeah, good point. Because supposedly, if evolution is true, we evolved from sea creatures.
Sea creatures, right.
So when we talk about the whale, talk about all the other things, we never talk about what's the whale eye like? Is it verted or inverted?
Well, that's a mammal eye. So it's
inverted.
Right.
Right, so they're talking about the whale would have, but he came from a sea creature, went on land, then came back to the sea.
And then you have a creature like the anableps, which has a split eye.
Yeah, that's
because
cool.
it's a fish that lives on the surface of the water,
Yep.
and the top part of the eye you can
Focuses
see
on the atmosphere.
on the atmosphere.
Bottom here is the refracted or the bent rays of the water. I know, and it can see how does the brain
And actually,
is a fish?
the most complicated eye is that
Oh yeah,
the
yeah.
trilobite.
Yep.
Trilobite eye is really complicated. And so we have all these different design types based upon the environment in which these creatures live. Now let's take a look at the optimum design of the inverted eye. It's a space-saving solution for small eyes such as fish. And fish have this inverted eye.
Oh, okay.
And so, like I said, one photon is enough to elicit a response, electrical response. And the eye is designed with what's called the fovea centralis. And that's the most sensitive part of the eye. It's when you're reading something or looking at it, and it's taking a look at a very small portion of the thing and focusing on it. And so even when you're looking at a letter on the page, your eye is sort of following it. It's looking at things like that. And so
Like you said, this allows us the ability to focus as well and to concentrate, as you will. Okay?
Right.
To do it, to narrow down like that. Okay.
And the human brain can see a cluster of 5 photons. Greater sensitivity might result in sensory overload. And so you mentioned that, you talked about that.
Okay.
And here's what happens when light hits a photoreceptor. There's a molecule called rhodopsin, I guess what it's called. And it changes in conformation.
Okay.
There's actually 2 different isomers of it. There's cis, which is sort of bent like this, and trans, which is bent straightened out. And
Then straightened out. That seems like
well, it's bent like this.
Oh, okay.
So it's so instead of having it on this side like this is when it's dark. When it's bright out, it bends up. So
it actually changes.
It changes in conformation. It's actually 2 different isomers of the same molecule, and so the rhodopsin straightens out when it hits the light, and it's that molecular change that causes the sensitivity to convert it into electrical signal that goes to the brain. Oh. Now how that works, I don't think I understand totally, or
it's beyond our pay grade at this point in time.
Yeah.
But does Jerry probably understand?
Yeah.
Yeah.
And there's a layer of cells called the retinal pigment epithelium.
Epithelium, yeah. Okay.
So the retinal pigment epithelium we'll call RPE for short.
Okay, RPE. All right. What does that mean?
That's a layer of cells that is right at the photoreceptor spot.
Okay.
And it needs to be on the outside of the eyeball because that's where the bloodstream comes in.
Okay.
And these cells, because they're continually changing as in response to light, they need to be continually watered and lubricated, and there's a lot of molecules that get disposed of, and so there's a lot of turnover in the terms of the cells that go on here. And so if they were inside the cell, you have to have some sort of blood vessel arrangement inside the eye for it to receive that. Now in the squid eye, I guess that's totally different the way that is handled.
Well, squids, don't they have really big, huge eyes?
They do have huge eyes.
Well, well, you're saying the inverted eye, the way we have it now, allows us to have the eyes. Otherwise, we'd be basically one big eyeball, or maybe two big eyeballs. Our head wouldn't be able to fit our eyes.
Well, I don't think that's necessarily the case.
No, I was wondering about that because you talked about how
the space saving,
the inverted eye is very efficient that way, you know.
Now, the rods and cones must face away from the front of the eye to be close to that vascular choroid, which supplies the photoreceptors with nutrients and oxygens. So if they were on the inside of the eye, it would disrupt the vision. So in this case,
okay, all right.
the cells that are in front of the light, when the light passes through these cells, but they're transparent. And so the brain straightens this all out.
It's amazing, I know.
And the other thing that I learned was that the blind spot actually has a function. And that function is that that becomes a focus for binocular vision. And so the binocular vision uses the blind spots to line up what the sensory is receiving from the brain receives in those two different signals, and then that focuses it into the three-dimensional.
You know, because three-dimensional vision, it's really, we can only see really three-dimensionally about 12 to 15 feet. And what the rest of it is, our brain shows either atmospheric or linear perspective. In other words, we start out with real stereoscopic vision of about 15 feet. But after that, it adds on, the information gets added on based on number one, your experience. That's why when you go out west sometimes, you can get fooled to think a mountain is only about a mile away when it's actually 30 miles away. Because the atmospheric perspective, it's so clear out there, you don't really realize how far away it is. After a certain point, it's very difficult. There was an artist, I can't remember what his name was. Might have been Magritte, one of those surrealist kind of things. And he had these, in France they had these ladders, they kind of bent up at the top. And he had it sitting next to a road, and the road, of course, in a two-dimensional picture, when you want to show perspective, you bend them kind of inward. It looks like things go out. And the ladder and the road looked like they were next to each other. It kind of really threw you off. It's just really realizing that's how two-dimensionally, when things get so far away, that's how your mind does it. But the first 10 or 12 feet, it's amazing. And you say that blind spot is what actually helps that work then.
Yeah, right.
So that actually real three-dimensional.
Now, didn't you make a sculpture way back in your days where it was made out of wires and you had to line up two different things, and when you lined it up, then it popped. You know, you had to...
Yeah, the sculpture was actually, I call it simply a table in the corner of a room. And what it was basically out of a metal rod, and it was welded together. And the corner came out like this, and it came out like this, but the table was bent, half of it was like two-dimensionally straight up, the other part went way back like this. But when you put it together, Doug, and you get right to the front of it, the table, both sides would look like they lined up, and the back would come, and the book was kind of floating in the middle, and it would look like all three-dimensional. Otherwise, it looked like a crazy TV antenna, I suppose.
Yeah, that's what it looked like.
It was really a wild-looking thing. But from front and back, two perspectives, didn't matter which, it would invert itself. Both front and back, it would actually become three-dimensionally a table in the corner of a room. But from every other perspective, it was just didn't look right. It didn't look right at all. And it was one of those fun designs, playing with perspective.
Now here's a little sub-chapter here that Jerry talks about. It says, does the backward design block inward coming light? And it says, nerve cell fibers and the small branches of the central retina artery and vein produce minimal hindrance to light reaching the photoreceptors. Since most cells are 70% water. Consequently, they're largely transparent. When viewed under the microscope, most cells are transparent. It's for this reason that stains such as eosin Y and hemoxylin 2 are required to better visualize the various cell parts.
Oh. Okay.
Although myelin, an opaque whitish lipid that coats the nerve axons, would block much light, in contrast to most peripheral nerves, the nerve fibers in the front of the retina are not myelinated.
Oh, myelin sheaths, we talk about that.
Yeah, and so these nerves don't have a myelin. Furthermore, the larger blood vessels and nerve fibers skirt around the area centralis where visual acuity is most important. And so that the vertebrate eye is highly effective in spite of the retina reversal because it's a precise visual instrument designed to function with rods and cones facing away from the light. And so, if you have the red blood cells that transport away transport the nutrients to the photoreceptors, they're poor conductors of light, and so they would block the vision.
Right, because they're covered with that myelin, you're saying, or is that something else?
No, that's the nerve. The red blood cells are part of the.
As you can see, this is complicated for me. I'm trying to figure this out, and so you as an audience, you might have to go through this a couple times. There's so many things in the eye. It's really. I get back to my basic thing with Darwin had. He was correct.
Yeah,
here's so complicated.
Yeah, here's Dawkins, what he has to say about it.
Okay.
Photocells point backwards away from the light. This is not as silly as it sounds. Since they are very tiny and transparent, it doesn't much matter which way they point. Most photons will go straight through and then run the gauntlet of pigment-laden baffles waiting to catch them. And so Dawkins admits this, okay?
Wow. That's because he didn't used to, I don't think. Maybe he always.
Well,
I don't know. I thought he did that same.
Well, he attributes this all to random chance processes, and
As I told you, the thing when we saw him at out here at Michigan State 15 years ago, 10 years ago, and he spent about an hour and a half trying to tell you why a jet plane's wing was designed, but a bird's wing was not. And a bird's wing is infinitely more complicated than a jet plane's wing. I mean, it's amazing. You know, I got done with that, and a bunch of the people that went with it, they were a little bit intimidated to go. When they got done, they go, "That thing didn't make any sense at all," and it doesn't really.
Well, it's fun to watch them. It was fun to watch him shoot himself in the foot when he was talking.
Well, he's honest enough. He's got an agenda. He's agenda driven. He's rejected the creator, understandably, but he's honest enough in some of his science thinking. He realizes when he gets caught, he's caught. Like the time when he was asked about the best evidence for increasing genetic information,
right?
You know, at the genomic level, and he couldn't give you one. He's honest in that respect, and he's at least willing to talk to people like that. Shermer, I like to call him Michael Squirmer, because he has to squirm around all the real arguments. He would never face Jerry Bergman. You know, he might be able to get me because I'm not as aware of this stuff, but he simplifies it to such an extent, Doug. It just reminds me they try to simplify arguments to certain cause and effect ways that just are not valid based on what you're telling me of what the eye needs to do to function properly.
Yeah, and I like to talk about the eye muscles.
Okay.
And you know, the eyelids, and you have eye muscles that can move the eye up and down and from side to side. But there's another, and so they have two sets of muscles coming from this side and two sets of muscles coming from here. But there's another one that sort of winds around the eyeball. And and it attaches onto one edge of the eyeball, and that's for if you tip like this and like this, your eyes rotate to accommodate that particular.
We know you in the audience are doing this with us now. We know you're doing it.
And so look in the mirror. If you look in the mirror and do that little move, you can see that your eyeballs stay level with the ground. And so that has to be coordinated with your ear, your semicircular canals, your balance, and so your brain works all that out. Now that's something I don't see in a camera happen.
No,
very
in
much.
fact, they do that. What they do on your iPhones and stuff. You know, every time you turn that thing, you're laying down, it flips sideways. I hate that when it does that. You know, I wish I could figure out so it doesn't automatically turn. But you know, you can set it, but they don't do that. It keeps flipping and it throws you off. You know, but your eye just automatically compensates.
The other thing that happens is that the lens of the eye is flexible, and so there's sort of like little muscles on the end of that lens that either stretch or.
What is the point of that?
Well, it helps to focus.
Oh, duh. Okay.
It helps.
Oh, yeah, that makes sense. Yeah.
In focusing on a certain thing.
Yeah.
And so if you're looking off in the distance or looking close, there's, that's the fovea centralis that I told you about. You're actually looking at a particular spot and trying to concentrate on that sort of thing. If he had all that light coming in and it was gathering all the light willy-nilly, well, then you have no point of reference. And so, except for this little spot, everything else is peripheral vision.
Yeah, you talked about that earlier before the show. I had no idea about that either. I just figured you knew you had rods and cones. One sees black and white, or the image in the cone, I guess, gives you the color sensory. But I didn't realize it was just that one little spot in there is the only straightforward thing. The rest of it's all around you.
So a little bit about this book before we go. I'll tell you what it's going to talk about: the design of the muscular skeletal system. The common complaint of the evolutionists is a bad back.
Oh.
And the second one is the design of the reproductive system. Now that one's a little bit fun. We'll have to do a show on that. And then the design of the nervous system, and this is the famous thing where the nerve from your brain goes down around your aorta and then comes back to your voice box.
Oh yeah.
And that's supposed to be a remnant of evolutionary.
Well, that reminds you of the tongue of the giraffe. I mean, it's different, but it just reminds me of that.
Well, I had one guy ask about that in an email, and I told him, hey, if you're such a good designer, why don't you surgically shorten that nerve and see what happens? Maybe the giraffe can sing. Well, with that, I hope you enjoyed our time on Revolution Against Evolution. We'll see you next time.
Bye.